Hello, my name is John Gabriel, and this is the New Calculus channel. I'm a lot more relaxed now than I was in my previous video. Perhaps I overreacted a little bit, but I've been called a crank so many times that it just hit a nerve, and I had to make sure that James R. Mayer understood who the real crank is. It's actually kind of unfortunate because if you read other parts of his website, he does see certain things correctly, and I wouldn't have called him a crank if I had seen some of his errors and noticed that he had the right ideas on many other concepts. It's actually unfortunate that people just don't pay attention to what they read. It's important to not jump to conclusions about somebody and to think carefully before you libel somebody else. Okay. Anyway, in this video I'm going to talk about something called the Manhattan distance paradox. It's not actually a paradox, like so many other things which are called paradoxes and are not in mainstream mathematics. And how I became aware of it was through an email that was sent to me by a mathematics teacher. And that's what I'm going to discuss in this video. So let's begin. What is the Manhattan distance paradox? Several years ago, I received an email from Kenny Felder, which you can read in the next slide. So we were corresponding back and forth about other things, and also about my new calculus. And in here, he says, okay, I don't know if I've asked you this before. I may have, because it's one of my standard questions to ask real math people, and I've never gotten an answer that I fully understood. Consider the following curve. And he describes a curve, which I'll show you in the next slides. And then he begins the premise for his question. He says, if you draw these, you can see that they are getting closer and closer to a diagonal line, but that the length of that line is not 12. It is 6 times square root of 2. I can make this more rigorous by rotating the whole drawing by 45 degrees. Now, each curve in the sequence is in fact a function, but Kenny doesn't notice that it's not a smooth function. I'll get to that later. It passes the vertical line test, and this sequence of functions is approaching a straight horizontal line, in fact converging uniformly towards it, but the arc lengths are not approaching the same value as the diagonal. What gives? Well, the answer is actually very simple. And if Kenny and others like he had actually studied the elements and understood geometry as one should understand it from the elements, this wouldn't have been a puzzle at all. So let's move ahead. So in this slide here, I'll just repeat that question so that you can see what he asked. And in the next slide, this is what he meant. He says, so if you take this length of 6 and that length of 6, and then you have them like this, and then like that, yeah, so 2 halves, the length of these arcs here is still 12. So, and subsequently the length of all these line lengths here in red are also 12. Okay, and his question is, surely it should approach 6 square root 2. Well, how can it approach 6 times square root 2 when it's constant? Okay, and this kind of shows you that infinity is a junk concept, because if you had to carry on doing this to infinity, the result would be unpredictable. In other words, you'd end up with garbage, just like you do with a lot of other concepts that involve infinity and which Cantor, the father of all mathematical cranks, used. And of course, the rotation of this by 45 degrees gives the function that Kenny was talking about. But notice the function is not smooth, okay? So consider here's the solution now. Consider that between any 2 points there are innumerably many paths. Between these 2 points, this one here and this one here, there are innumerably many paths. However, only one of these paths is the shortest distance. That is a straight line. So this is the simple geometric explanation. Kenny missed it, and many others missed it. In his example, he found a special set containing the number of ways to make up a sum as a linear combination, 12, which uses distances that are a factor of 6. And to interpret that as a limit would be completely wrong, as we've seen here, okay? So that's the simple explanation, both geometrically and algebraically. You can't interpret that as a limit. There is another site called Troll Pi. Well, it has an article on pi being 4 instead of the actual value, whatever it is. So that site uses a similar pseudo-argument to the Manhattan distance argument, where it tries to show that the actual value is 4, but it's not correct because the reasoning and the arguments are wrong. So the function that converges to the diagonal is not a smooth function. For if it were, the distance would not remain constant. Think about that. If you took a sine wave and you decreased its amplitude and period uniformly, the distance of the arc length would approach the length of the diagonal. Pay attention to the next statement, because most mainstream, in fact, every mainstream academic I've ever met doesn't know this fact. Calculus works if and only if the given function is both continuous and smooth. Okay, so that sawtooth function that you saw earlier on that Kenny pointed to does not have the same properties as a smooth and continuous, or a continuous and smooth function. And the methods of calculus are designed to work only on continuous and smooth functions. And this is something that most mainstream orangutans do not understand. So I've tried to explain that as simply as I could, and I think I didn't do a very bad job of it. I hope this puts this fall paradox to rest, because it's not a paradox, it's really just garbage. And hopefully you'll join me again in another video at some future time, as and when the Spirit moves me. I'm not really religious, I just use that saying. In any event, this is a new Calculus channel. I'm John Gabriel. Till next time, goodbye.